Hello, friends. In today's lecture, in our hydraulics and hydraulic machines class, let us discuss on one of the most important topic, the maximum speed of the reciprocating pump. Very, very, very important. What is the equation or method to find out the maximum speed of the reciprocating pump? This maximum speed of the reciprocating pump can be obtained based on one simple fact. The pressure head in the cylinder at any instant of time, that means during suction stroke or during delivery stroke, the pressure head in the cylinder should not fall below the vapor pressure of the liquid which is flowing in the suction pipe and delivery pipe. In other words, if you take that liquid as water, the pressure head in the cylinder, either during suction stroke or delivery stroke, anytime, should not fall below the vapor pressure of the liquid, I say water, flowing in the suction pipe or delivery pipe. Because whatever that flows in the suction pipe, that only will flow in delivery pipe. This is the simple principle on which the whole derivation is done. Why? If the pressure head in the cylinder is less than vapor pressure of the liquid, what will happen? You all know number of times, starting from fluid mechanics, we discussed about it. If the pressure at any point falls below the vapor pressure of the flowing fluid, what will happen? The dissolved gases gets liberated, formation of vapor bubbles. These vapor bubbles, actually the movement of vapor bubbles gives rise to cavitation, gives rise to cavitation phenomena. So that is why the fundamental principle in fluid mechanics or hydraulic machines anywhere, the pressure at any point should not fall below the vapor pressure of the flowing fluid. Whether it is pipe, whether it is in reciprocating pump, centrifugal, anytime, anywhere, it should never fall below the vapor pressure of the flowing fluid. The moment it falls, the effects of cavitation will be different based on different processes you are handling. In turbines, if we see that, the turbine runner blades gets spoiled. In centrifugal pump, if you see that, the impeller blades are spoiled. In the case of venturimeter or any pipe, if you see it, there will be high impact pressure on the pipe. Cavities are formed on the pipe inside. So these are all the effects. So that is why the moment this cavitation occurs, flow continuity will not be there. Flow gets separated. The flow separation leads to eddy currents. Flow separation leads to this, the what you call it as the discontinuity of flow. This leads to efficiencies fall down. So that is why if you want to make the flow continuous, the maximum speed of a reciprocating pump should be such that the pressure head during suction stroke or during delivery stroke at any crank angle theta, it should be less. It should not be less. Again, remember, it should not be less than the vapor pressure of the flowing fluid. That's the principle on which let us go and write the equations and study. Maximum speed of reciprocating pump. That is so. What is the condition actually? Pressure head in the cylinder of the reciprocating pump during suction stroke or delivery stroke. It should not fall down below the vapor pressure head of the liquid flowing in suction pipe. Am I right? Once again, read the pressure head in the cylinder during suction stroke or delivery stroke. What I have written, you see, less than vapor pressure head of liquid. It should not. This is the important point. Should not. Very, very important. Should not be low. The vapor pressure. So it should not be less than, it should not be below. The meaning of this is should not below the vapor pressure of the flowing fluid. Now, if you take it, for example, suction stroke, just recollect. If you want to draw, once again, you draw, no issues. Draw the indicator diagram showing all the effects, right? If you want me to show just like this on this side, rough diagram, I will write stroke length. This is pressure head. For your understanding sake, this is H atmosphere, right? We know basically. Finally, this is our initial thing, right? Then our next thing is like this. This is the thing which we got, right? The final thing which we got it is this, this. So this is how the diagram is. Now, if I see this diagram, pressure head is minimum. This is atmospheric pressure head. Pressure head is minimum at the beginning of suction stroke. Which is equal to Hs plus HAS. Whereas at any other, at the middle, if you take it, it is just basically what you call it as Hs basically plus HFS. Hs minus HAS. So if I see out of all, naturally Hs plus this is minimum. This is Hs plus HAS. Here this is the minimum basically. So if I take it, this pressure head here, what is the absolute pressure head? Absolute pressure head is equal to, because this pressure head is less than atmospheric pressure, it is equal to H atmosphere. So absolute pressure head means this, H atmosphere minus Hs plus HAS. This absolute pressure head basically, right, should not fall below the vapor pressure of the fluid. Suppose now I take the liquid as water. For water, if I take it, actually the vapor pressure head is equal to 7.8 meters of water below atmospheric pressure or 10.3 minus 7.8. It is equal to 2.5 meters of water. Absolute. So this is what I mean by. So now our question is actually, so when this condition, when the pressure falls below this, that means if the absolute pressure at the beginning of suction stroke should not fall below the vapor pressure of liquid flowing. If it falls below vapor pressure, cavitation occurs. If cavitation occurs, flow separation takes place. If flow separation takes place, no continuity of flow. So this is the problem. So this basically, what we call this, this vapor pressure, we call it as separation pressure. Separation pressure head. This separation pressure head is nothing but the vapor pressure head actually. The separation pressure head is nothing but the vapor pressure head. Why? Because the why I am writing separation straight means because vapor pressure people. So finally, what for we are doing it? Separation should not occur. If the speed should be such that there will be no separation of flow. So this the where if it the separation occurs, that is what I call it as H separation. So if I apply it to this pressure at the beginning of suction stroke should not basically, that means H separation is equal to what I call it as what is happening? It is H atmosphere minus HS plus HAS. This is the thing. So if I take it like this, what is HAS is equal to this, I take it on that side. So it is H atmosphere minus HS minus H separation. This H separation is the vapor pressure of the liquid flowing. So this is in terms of we are writing it absolute. So therefore, we know what is Hs is equal to at the beginning of suction stroke. Hs is equal to Has is equal to omega square r as cos 0 is equal to 1. So this is equal to H atmosphere minus H separation. Now in this, if I see Ls is known, right? A is known, AS is known, basically, right? R is known, H atmosphere is known, HS known, H separation known. Only unknown is omega. So find omega and hence the speed n, which is equal to, and the relation you know, omega is equal to 2 pi n by 60. So using that, you can find out. So this is the basic thing. So we got the speed. So keep it. That is the first thing. So during this, what we understood finally, during the suction stroke, if at all this, the what you call it as separation occurs, right? It is only at the beginning of suction stroke because the pressure is minimum at the beginning of suction stroke. So if at all that separation occurs, it will be only at the beginning, right? That means when theta is equal to 0 degrees. So that is why what is the pressure head we are finding it out. That absolute pressure head is equal to, this is the absolute pressure head, which is equal to this actually. So that is what which we have found. Then actually what we mentioned, this absolute pressure head, what is the condition actually? The pressure head should not fall below the vapor pressure of the flowing fluid. For any liquid, whatever it is given, we know the vapor pressure. So we convert that and keep actually in absolute pressure units. Then afterwards actually, so what is the condition that which we are going? This minimum pressure, whatever we are talking about, that pressure head should not fall below the vapor pressure head. But what happens if it follows? cavitation occurs. What happens if cavitation occurs? Liquid flow, the flow gets separated. What happens if the flow gets separated? There will not be continuity of flow. So that is why this vapor pressure head is called as separation pressure head. So that is why, that is what I have put, separation pressure head. Therefore, separation pressure head is equal to atmospheric pressure head minus all this. Because this is vapor pressure head is equal to this, that's why. Actually, this vapor pressure head should be more than this. Now, whatever you are getting, this head, not vapor, this head H atmosphere minus HS plus HS, this all should be greater than the vapor pressure head actually. If it is greater than vapor pressure head, there is no problem. Because it is, if it is, it should not be less, but at least if it is equal, there is no issue. That's why I have put G equal if the for the separation pressure head. So I write that, and then we know what is HAS is equal to at the beginning of suction stroke when theta is equal to 0, cos 0 is equal to 1. Therefore, LS by G, A by AS into omega square R basically. So everything in this except omega we know. Only thing is we need to find out omega. Once you find out omega, find out the speed. This is the first thing. Then I will go to the delivery stroke. Please remember the minimum pressure during in the delivery stroke. Minimum pressure in the delivery stroke will be at the end of delivery stroke. Right? If you take at the beginning of delivery stroke, HD plus HAD. At the middle, HD plus HFD. HFD will be always very, very, very less. Whereas at the beginning, you take it HD plus minus HAD. HD minus HAD. So what is the pressure head? At the end of delivery stroke, it equal to HD minus HAD. Absolute pressure head. Absolute pressure head at the end of delivery stroke is equal to H atmosphere plus, because it is above atmospheric pressure head, HD minus HAD. So therefore, this absolute pressure head actually should always be greater than the separation pressure head, or basically at the max it can be equal. So if I equate it, H separation is equal to H atmosphere plus HD minus 1. Therefore, HAD is equal to H atmosphere plus HD minus H separation. What is HAD? The HAD at the end of delivery stroke. That is theta is equal to 180 is equal to LD by G A by AD omega square basically R. Already this minus sign I have taken it up in the beginning itself. That's why here I have written minus HAD. So this is the thing. So in this now LD by G A by AD omega square R is equal to H atmosphere plus HD minus HAD. Not HAD, sorry. Separation. Already H. So this H separation we know depending on the vapor pressure of the fluid convert into absolute and you can put it. HD we will be knowing it and H atmosphere is 10.3 meters of water absolute. That is okay. Then LD is known, A is known, AD is known, R is known, unknown is only omega. So unknown is only, so therefore find omega and hence n. Just for your understanding sake, when the separation occurs in delivery stroke is if suppose the acceleration pressure head is so high, even it crosses HD, then at that time actually even it has to cross HD, it has to cross H atmospheric pressure. So both the things and it becomes a negative. The acceleration pressure head is so high so that because it is negative side on that one, theta is equal to 180. So if at all that occurs this. So that's why the now if you see overall now there are two speeds. There are two speeds. One is calculated based on minimum pressure during suction stroke. Second is based on minimum pressure during delivery stroke. I told already this will be at the beginning and this will be at the end. Right? There are two speeds. This is one speed, this is one N, this is another N. So two speeds are there. Now out of the two, the minimum speed will be the maximum speed of reciprocating. Just for example, so if you found out the one speed is 200 rpm, sorry, one why, 100 rpm. Second one is 70 rpm. Out of this, whichever is minimum, this mean will be the maximum speed of reciprocating. Actually, on this, the problems are being asked in the semester and examinations. Kindly remember what you have to calculate. Just simple actually. Just remember the equation. H separation is equal to, basically you need to write whether it is suction stroke or delivery stroke, the whatever is the pressure. So what about is the pressure? You write it at the beginning. At the beginning, if you write it, it is H atmosphere minus of, in brackets, Hs plus HAS, and this is equal to H separation. Put that, then bring HAS on left hand side and write the equation LS by GA by AS into omega square R, and then find out what is the speed. Similarly, go to the delivery stroke. You know what is HD, basically write the equation HD basically minus HAD, and this is above atmospheric pressure, so thereby you have to write it actually. You need to write it is H atmosphere plus HD minus HAD. So that is equal to the separation pressure head. So now HAD you bring on left hand side, and it is LD by G into A by AD into omega square R. So everything is known except omega. Find out omega. Now there are two speeds to you. Out of these two speeds, whichever is the lowest, whichever is the minimum, that will be the maximum speed of the reciprocating pump. I have seen at least twice this problem is given in the semester and examination. Please prepare well for this problem actually. Right? With this, I have completed one more top part of the reciprocating pump. There is only very small part that is left over, that I will take it in the next class. Thank you.
Like, share, and subscribe. Hit the bell icon for more updates.